Hello everyone. Today we're discussing the first hands-on experiment you'll be working on in the lab called Basic Lab Operations. It's experiment 1. And what I'm going to do is basically run through the report sheet, give you some pointers on filling it out. The experiment itself is fairly straightforward, and hopefully you won't have any trouble with it. The experiment is designed to make you more comfortable around the lab and learn how to use various basic laboratory equipment that we use here on an everyday basis, including balances, measuring pipettes, and things like that. So one thing I'd like to do is the first part, which says Bunsen burner, we're going to skip for now because I don't know if there will be enough time. I want to make sure you have enough time in this lab time to do 2 experiments, both experiments 1 and 2. And so we're going to skip Bunsen burner for later, and if we find that you do have enough time, we will quickly show you the use of the Bunsen burner and demonstrate. Otherwise, we'll just do it in the next lab. So you're going to start with part B, which is laboratory balances, and we will try to have TAs do a demonstration in small groups showing you how to use balances. I did show balances that we have in this lab briefly in the lab walkthrough, and I did mention, I believe, that balances are all milligram balances, meaning they allow you to weigh to the nearest milligram or 1,000th of a gram. So you should always have 3 significant figures after the decimal for all mass readings you ever record in this lab, not only in this experiment, but in all future experiments as well. And so what you're basically going to do is you're going to weigh various objects from your drawer. If you look at page 65, that's where report sheet begins. And for part B, it lists various objects such as test tube, beaker, spatula, graduated cylinder. For description, you can pick any test tube. You have 2 various sizes of your test tube, either medium or large. So you can just write either medium or large for description of that. For beaker, you have 6 beakers. You can use either one of those 6. The smallest one you have in your drawer is 50 milliliter one. The largest is 600. So just write down the volume of the beaker that you picked. Spatula for graduated cylinder, you also have a couple of options. There are 2 graduated cylinders in your drawer, the smaller one, which is a 10 milliliter one, and the larger one, which is a 50 milliliter one. And then it says other. Here you can pick any other object from your drawer to weigh, such as, for example, evaporating dish or a casserole or some other piece of equipment, or watch glass for that matter. So basically it's just an exercise in weighing and properly recording your mass to 3 digits after the decimal each time. I also mentioned, I believe in the walkthrough video, that all our balances have a tare feature, so you'll be able to use that feature if you need to, but in this portion you will not. Next, part 2 of part B is precision of measurement. Precision has to do with getting same measurement every time. If you measure same exact object, you would probably say, well, common sense tells us that mass should be the same if we're weighing the same object more than once. True, but each balance is not an ideal machine. It's an instrument that may have certain things influence how it measures. For example, airflow, if we close or open hoods, may influence whether balances gives the same value of mass of the same object. So here what you're going to do is you're going to take your small 10 milliliter graduated cylinder, you're going to weigh it empty and record its mass to 3 digits after the decimal. Then you're going to place about 7 milliliters of water into the cylinder, and then you're going to weigh it again. And then you're going to record the total mass of cylinder plus 7 milliliters of water. Then you're going to empty the cylinder. You're going to pour the same amount of water as before into it and weigh it again. Now, at the bottom of page 65, they want you to do this 6 times. I do think it's a bit excessive, and we want to save time. So we only ask that you do 3 trials for this. So you're going to put the water in and weigh the cylinder and record the mass, and you're going to do this 3 times. And then it says on the very bottom of the page, it asks you to find the average mass of 7 milliliters of water, and then comment on the precision of the mass measurements. So basically, briefly, in one sentence, please tell us whether you think precision was good if you got very similar answers, or maybe precision wasn't so good if your answers differed by a lot. I hope it is obvious that in order to find mass of 7 milliliters of water, for each trial you're going to subtract mass of empty cylinder from the total mass of cylinder plus water. Moving on to page 66, this is where we're going to be talking about density. And just to review, density is found as mass over volume. Units for density are grams per cubic centimeter or grams per milliliter. These are the same numerically because 1 centimeter cubed is equal to 1 milliliter. And so for density, first we'll work with solids. Those will be pieces of metal that will be provided by your TA, various metals and or alloys. Each of you is going to get 1 piece. Make sure to record its identification number on your on your report sheet. The identification number will be scribbled on its side. And then you're going to weigh the piece and you're going to record the mass to 3 digits after the decimal, as demonstrated here in my example. And then to find the volume, you're going to use displacement method. So you're going to take a small graduated cylinder, you're going to fill it with water about halfway. You're going to carefully read the volume, initial volume of water to the nearest 0.05 milliliter, and then record it, and then carefully place the solid in the cylinder. Don't dump it in there because some metals are heavier than others. It's possible if you plunge that metal from high up, you may break the glass. So carefully slide in the piece. Obviously, according to displacement method, the level of water will rise, so you will read the new volume and then find the net volume of the solid by subtracting initial volume from final, and then you'll be able to calculate density. So in my example, I'm giving volume of net volume of solid, so this will be a product of subtraction of initial from final. And if your mass was say 3.426 grams, now don't read too much into these numbers, it's just totally made up these numbers on the fly. And let's say the volume of solid was 0.45 milliliters, then your density would have to be calculated with proper number of significant figures. That's very important. It will be part of your grade. And in this case, I did the math. 3.426 divided by 0.45 gives me, here I have total of 4 sig figs, but for my volume I only have 2 sig figs. So my density must be rounded off to 2 sig figs, or 7.6 grams per milliliter. And then another example, what if my volume was greater than 1, then I would have a total of 3 sig figs. Like in this case, my volume is 1.30 milliliters. And let's say my mass was 8.279 grams, then my density should be calculated to 3 sig figs, because my volume has 3 sig figs here, and I would record my density in this instance as 6.37 grams per milliliter. Now, just to explain how volume is read using a 10 miller graduated cylinder. So in a cylinder, your highest number is 10 and your lowest number would be 1. I don't think it has a graduation mark for 0. And so here you're reading from bottom up, and the graduations, you have milliliter graduations, like this is 10 and this is 9. And typically in the graduated cylinders found in your drawers, you would expect to find 10 graduations in between each milliliter mark, meaning the distance between 2 nearest graduation marks here would be equal to 0.1 milliliter. And so you expected to evaluate the location of the bottom of the meniscus Meniscus, of course, is the curved line liquid makes in a narrow container. And you always look at the bottom of the meniscus. Remember to set the graduated cylinder down on the flat surface like your bench, and lower your eyes so you can clearly see where the meniscus is. There are basically two and only two possibilities here. One is meniscus is right on the line, like in this example here, in example A. Or the second possibility is meniscus being in between two lines. Regardless of whether the meniscus is closer to the bottom line or the top line, you still read it to the nearest 0.05 milliliter. Meaning, in this case, this is 9 milliliters, this is 10. So we're counting from bottom up. 9.1, 9.2, 9.3, 9.4, 9.5. The bottom of the meniscus is right at 9.5 milliliter mark. So the volume I would record would be 9.50. This zero here is considered significant because it shows the degree of confidence you have in your measurement. You clearly see that bottom of the meniscus is on the line. So volume recorded properly for this type of situation would be 9.50 milliliters. For example B, I have my meniscus in between these two lines. Again, we're counting from the bottom up. So this is 9.0, this is 9.1, and this is 9.2. Meniscus is in between 9.1 and 9.2. Remember, we're reading to the nearest 0.05 milliliter. So for this example B, correct reading would be 9.15 milliliter. So whenever you're reading your volume using a small graduated cylinder, you should remember that your volume must have 2 digits after the decimal. Second digit being either 0 when meniscus is on the line, or 5 if meniscus is in between the lines. And also for density readings, you're expected to do density of liquid. That's part C 2 and 3. Here you're doing first density of water and then density of the unknown liquid. So to do density of water, you're going to pour some water into a beaker of any size you wish, and then you're going to measure a certain aliquot or fixed volume of water into a pipette. What I have here is a 5 milliliter graduated pipette. You may be given similar pipette to this one, or a 10 milliliter pipette. I'd like to point out that density is the type of property that does not depend on the size of the sample, right? So mass, of course, depends on the amount of material you have. Volume also depends on the amount of material you have. Density does not. So the exact volume that you measure is not important. What's important is you measure it accurately as possible. And what I would like to point out here is that pipette is very different from a graduated cylinder in the way how the numbers on it are positioned. In a graduated cylinder, the number on the very top is 10. Here, on the other hand, in the pipette, the number on the top is 0. And the number on the bottom is 5. So this is again a 5 milliliter pipette. You may be given one that has 0 on top but 10 on the bottom. That would be a 10 milliliter pipette. Regardless of that, the thing to remember is you always must fill the pipette to 0. And then when you measure, you empty the pipette. And the further down you go, the larger the volume you will have dispensed. With this particular pipette, you cannot dispense more than 5 milliliters. 5 would be the top amount you can, maximum amount, I should say, you can dispense at once with this particular pipette. But the thing to remember is here we're counting from from top down. As we go further down, the numbers will increase. The graduations are similar to those in graduated cylinder we just discussed in the way how they are done. So they're done in milliliters. So this is 0, 1, 2, 3, 4, 5, and so on. There are 10 graduations in between each milliliter mark. That's similar to graduated cylinder. So the distance between two nearest graduation marks here is also 0.1 milliliter. So what I did over here is I showed how to read a graduated pipette. I wrote 10 milliliter, but it could be 5 milliliter also, it doesn't matter. So here I have 0 on top, and assuming I fill the pipette all the way to 0 first, and then I'm starting to dispense. Let's say I dispensed from 0 and I stopped right here, and my meniscus is right between these two lines. What volume would I record? Remember, in this case, volume increases as you go down. So if this is 0, this would be 0.1, this would be 0.2, this would be 0.3. My meniscus happens to be in between 0.2 and 0.3 graduation marks, so the volume I would record would be 0.25 milliliters. Once again, reading volume to the nearest 0.05 milliliter. Here in part B, or example B, my meniscus happens to be right on the line, and it's right above 1 milliliter. So if this is 0 and this is 1, this would be 0.9. And so in this case, in example B, my volume recorded properly would be not just 0.9 milliliters, it would be 0.90 milliliters. This 0, once again, would be considered significant because I have confidence in the location of my meniscus. You will be using so-called 3-way pipette bulb that will be placed on top of the pipette, which would allow you to draw liquid in and out of the pipette. Never ever use your mouth, even if it's just water. Mouth should never be used, and the use of this 3-way bulb will be demonstrated in class, specifically right before lab, by either me or one of the teaching assistants. So going back to your report sheet, we're looking at page 66. For density of water, you're going to do 2 trials for water, and then you're going to find the average density of water, and then you're going to ask other students in the class to give you their densities of water values so you can do class data group analysis here, and then your TA will tell you which unknown liquid you're supposed to use. Using same pipette and clean dry beaker, you're going to get some unknown liquid from the hood into a beaker, and then use a pipette to measure a certain amount into a separate clean dry beaker, which then will be weighed to find the mass of that sample of liquid. Again, I'd like to emphasize that for both water and liquid, the exact volume that you measure is not important. You can measure 5 milliliters of liquid, either water or unknown liquid, and then find its mass, or you can measure, say, 10 milliliters. It wouldn't matter because density is something that it's a type of parameter, I should say, that does not depend on the size of the sample. So depending on what volume you measure, mass will reflect that volume. So dividing mass by volume should then give you accurate density. I would also point out that hopefully everyone knows the density of water is expected to be 1.00 grams per milliliter. So hopefully when you do your measurements, you keep in mind that that's what density of water is. So if you try to tell me the density of water was found to be 10 grams per milliliter, I'm sorry, but I'm not going to believe you. And so you have to kind of have an idea of realistic parameters such as density of water that you're trying to find. That's all.